The second derivative and its interpretation. Consider the function y equals x cubed minus 3x. It's a cubic graph, so it's S-shaped. The derivative of this function, dy dx, equals 3x squared minus 3. And it's a U-shaped graph. This gives the slope of the tangent at any point on the curve y equals x cubed minus 3x. It may also be regarded as an expression for the rate of change of y as x changes. So the derivative of a cubic function is a quadratic function. So the derivative of an S-shaped graph is a U-shaped graph. But dy dx equals 3x squared minus 3, so our U-shaped graph, is a curve in its own right, and as such has tangents which have slopes. Once again, the slopes of the tangents can be found by differentiating. This can be written dy dx equals d 3x squared minus 3 dx, which equals d squared y dx squared, which equals 6x. So basically, if we differentiate 3x squared minus 3, we get 6x. So the derivative of this curve, this U-shaped graph, is a straight line. And it is 6x. This derivative of the derivative is written as d squared y dx squared, or as f double prime x, and is referred to as the second derivative. So to get this 6x, we differentiated the cubic function and we got a quadratic function, and then we differentiated again and we got a straight line. So this second derivative may also be referred to as the slope of the slope function, or as the rate of change of the rate of change. One example of the second derivative in real life is that of acceleration. The acceleration of an object, for example a car, is the rate of change of the velocity. But velocity is the rate of change of the distance. Hence, acceleration can be considered to be the rate of change of the rate of change of the distance, i.e. a second derivative. We will investigate this in more detail in the next chapter. When there is any doubt as to which derivative is involved, dy dx equals f prime x can also be referred to as the first derivative. In practice, the methods and rules used to find the second derivative from the first derivative are the same as those used to find any derivative. For example, standard derivatives, product, quotient, and chain rules. So, if f of x equals the distance, then f prime x, the first derivative, equals the velocity, and f double prime x, or the second derivative, equals the acceleration. Example, if y equals x sine x, find d squared y dx squared. So basically find the second derivative. So we get dy dx first, which is the first derivative, and differentiate again to find d squared y dx squared, the second derivative. So y equals x sine x. So these are stuck together, which means multiply, so we use the product rule. So we get x times cos x plus sine x times 1, which gives us x cos x plus sine x. Next we want to differentiate again. So again, we're going to use the product rule, this time for the x cos x, and sine x we can just differentiate straightforwardly. So using the product rule to differentiate x cos x, we get x times minus sine x plus cos x times 1, and differentiating sine x we get cos x. And simplifying, we get minus x sine x plus 2 cos x. The sign of the second derivative. The sign of the first derivative, dy dx, tells us whether the curve y equals f of x is increasing, positive, or decreasing, negative. What does the sign of the second derivative tell us about the curve y equals f of x? The sign of the second derivative tells us about the curvature of the curve, i.e. which way the curve is facing. The curvature is generally described in terms of which way the curve is concave. There are two possibilities for a curve which is everywhere differentiable on an interval: concave upwards and concave downwards. So the first derivative, if it's positive, the curve is increasing. If it's negative, it's decreasing. The second derivative, if it's positive, it's concave up. If it's negative, it's concave down. So concave upwards. The curve y equals f of x is concave upwards between the points A and B if every line segment joining 2 points on the curve between A and B, for example CD, lies completely above the curve. So this U-shaped graph here, this U-shaped curve, is y equals f of x. And this curve is concave upwards between A and B if every line segment joining the 2 points on the curve between A and B, for example C and D, there's a line segment, lies completely above the curve. So basically if it's U-shaped. If the derivative dy dx is increasing at all points between A and B, then the curve y equals f of x is concave upwards in this region. So here we have the derivative f of f prime x, and we can see that it is increasing. It's going upwards. Thus, if dy dx is greater than 0, which basically means d squared y dx squared is greater than 0, so if the second derivative is greater than 0, then the curve is concave upwards. So up is U-shaped. Concave downwards. The curve y equals f of x is concave downwards between the points A and B if every line segment joining 2 points on the curve between A and B, for example CD, lies completely below the curve. So here we have the graph y equals f of x. It's N-shaped. And here we have the point A and the point B. So the curve is concave downwards between A and B, so between these 2 points, if every line segment joining 2 points on the curve, for example CD, lies completely below the curve. So basically N-shaped with concave downwards. If the derivative dy dx is decreasing at all points between A and B, then the curve y equals f of x is concave downwards in this region. So here we have dy dx, so the derivative, and it is decreasing, it's going downwards. Thus, if dy dx is less than 0, or d squared y dx squared is less than 0, so basically the second derivative is less than 0, then the curve is concave downwards. So to summarize, curvature, a curve is concave upwards where the second derivative is greater than 0, and a curve is concave downwards where the second derivative is less than 0. It's important to learn this off. Show that the curve y equals e to the power of x is concave upwards for all x values elements of the real number set. Any mention of concave means that we have to look at the sign of the second derivative. So y equals e to the power of x, dy dx equals e to the power of x, and d squared y dx squared equals e to the power of x. So as e to the power of x is greater than 0 for all x values elements of the real number set, and the second derivative, d squared y dx squared, is greater than 0 for all x values elements of the real number set, hence the curve is concave upwards for all x values elements of the real number set. Because a curve is concave upwards when d squared y dx squared is greater than 0. So when the second derivative is greater than 0.